Hello, this is mathjazz from Almost Cool. This is the 6th video in our series of videos on limits. Our topic today is continuity. The definition of continuity is a function f is continuous at a if f of a equals the limit as x goes to a of f of x. That is, if the limit of the function at a is equal to the value of the function at a, then f is continuous. This is why we had the conditions x sub n is not equal to a and 0 is less than x minus a in the two different definitions of limit in the previous videos in this series. If we forget these conditions, we actually give a definition of continuity and not a definition of limit, because lacking these conditions forces f of a to equal the limit. So the function must be continuous in the absence of these two clauses in the definition of limit. Intuitively, a function is continuous if the graph of the function is able to be drawn in one pencil stroke. Also intuitively, continuity is a prohibition against teleportation. The path of a traveling particle is continuous if the particle never teleports or ends up in multiple locations at the same time. Here are some examples of discontinuities. This is a removable discontinuity. It's called a removable discontinuity because this gap here can be removed by dragging the value that the function has, up here at this colored in dot, down to be in line with the rest of the function. That's another way we can kind of think of continuity, is that a function is continuous if kind of at every point the function points to its own value at that point. So like if we're looking at this point, it looks like 0.7 here is where the gap is. The function points to this value where this hollow circle is. That's what we would like the value of the function to be. If we want the function to be continuous, that has to be the value of the function. But the value of the function is actually up here above that hollow circle. And so this is not continuous at that point because that's not what the function is pointing to in some sense. And see, if we look at any other part of the function, it's continuous there because we have no weird gaps or jumps or breaks in the graph. But at that point, at x equals I guess it's 0.8, not 0.7. But at that point, the graph is discontinuous because we have this gap here. And the value of the function is different from what the function is pointing to, again, in some sense of the word point. The next three examples are examples of irremovable discontinuities. So removable discontinuities can be fixed by just saying, oh, well, let the function's value be changed to its limit's value. But irremovable discontinuities are different in that the limit doesn't exist. So, as we said, the definition of continuity is the function's value equals its limit. So removable discontinuities are cases when the value just doesn't equal the limit, but the limit exists. So if we change the value to be the same as the value of the limit, we'd get a continuous function. We could remove the discontinuity. With irremovable discontinuities, however, the limit does not exist, which means we cannot just redefine the function's value at that one point to fix the problem. Here's an example of, it's called a jump discontinuity. It's one of the three types of irremovable discontinuities. And as we see, here's a little particle. It's going to travel along this path, but to travel along this path, we have to have the particle teleport. So this break in the graph, there's no way to draw this with one pencil stroke. Anything that's traveling along this path has a teleportation to be able to travel along the path. This is discontinuous, and we see that the limit also does not exist at x equals 0. It's kind of relaxing seeing these dots bounce back and forth on these these graphs. But we have another graph to look at. What's coming up next is called an infinite discontinuity. In some cases, this is called an asymptotic discontinuity. If the infinite limit is in fact an asymptote as well, it's called an asymptotic discontinuity. And we see here, again, the point has to teleport to get from down near negative infinity on one side to up near positive infinity on the other. Same thing happens actually if the graph goes up to infinity or down to infinity on both sides, is that you still have to jump from one section of the graph to the other, which means that you're still having an infinite discontinuity, even if the limit from the right and the limit from the left are both infinity or both negative infinity. Now, the next discontinuity we're going to show is not usually found in textbooks. I mean, there are some calculus textbooks that talk about oscillatory or oscillating discontinuities, but I find that that's the minority of textbooks that talk about these. In this case, what happens is that dot actually has to be in an infinite number of places when x is 0. So it's not exactly teleportation, in that it's not disappearing from one spot and appearing somewhere else, but it is appearing in multiple places at the same time. And so this is also a discontinuity. And this is irremovable. There's no way to just redefine the function at x equals 0 to make this fixed. And this is an irremovable discontinuity, and these are the 3 different examples that we can have of irremovable discontinuities. So, thank you for watching this video. I hope that you're enjoying learning calculus. Our contact information is on the screen, if I can get the screen to line up again. There we go. And it's also, the contact information is also down below in the description of the video. I hope that you have a great day. Goodbye.